Hey guys, so this question reads that a particle with charge Q moves horizontally with a speed v in the presence of a uniform vertical electric field. Determine the magnitude of a uniform magnetic field B that could result in zero net force on the moving charge. So I've drawn out the scenario for you, and it doesn't necessarily tell us whether it's moving right or left. So in this case, I just made it moving to the left. You might have imagined it moving to the right, but that's not really what's important here. Looking at the solutions, we can see that we're not looking for a direction or anything like that. We're not looking for a value. We're more relating to, we're looking to relate the forces. And I'll explain what I mean by that a little more. So this uniform electric field that's moving upward, moving vertical, is going to have a force on this particle. And if it's a negative particle, then it's going to have a force that's moving upward, like that. And that force can be determined by the electric field equation, which is that an electric field is equal to the force over the charge. And so this force here, this electric field force, is this F variable right here. So what we want to know is what is the magnitude of uniform magnetic field that could result in a zero net force. And we know conceptually that a magnetic field has the ability to produce a force. And so what we're looking for is what is the magnitude of that magnetic field that is going to create a force that is going to balance out this electric field force. So in other words, we want to know a force moving downward from the magnetic field. What is the magnitude of that magnetic field? Well, that force value can be determined by the equation force is equal to charge times the speed or the velocity times the magnetic field times the sine of theta. And so now we see that we've got both forces, one for the electric field and one for the magnetic field. And what we're going to do is we're going to relate them to one another. We're going to set them equal to one another so that we can get a zero net force because they're going to be going in opposite directions. So let me go ahead. We're going to isolate the force over here, which we're just going to multiply both sides by the charge. So force is equal to electric field times charge. And then over here, the force is already isolated. So next thing we're going to do is we're going to set them equal to one another. We're going to set the forces equal to one another because that's how we're going to get a zero net force. And then now the next step we'll take is we're going to cross out like variables, which is charge, because we're dealing with the same particle. And then another thing we need to take out of here is the sine of theta. And because this is where the vertical electric field is important, because since it's vertical, it's technically 90 degrees above the horizontal. And so the sine of 90 degrees is equal to 1. And so we can just cross this out and imagine putting a 1 there, which isn't necessary. So we get that. So then what we end up with is the electric field is equal to the velocity times the magnetic field. And what we're looking for is the magnetic field. So then all we need to do in this case is divide both sides by the velocity. And we get that the magnetic field, I'll go ahead and do that in a different color. The magnetic field is equal to the electric field over the velocity, which is answer A. So just to recap, the way we got that is by recognizing that one of the forces from the electric field is going to be moving in either up or down direction, because this is just the way I drew it, but it just tells us that it's vertical. It doesn't tell us whether it's a positive or negative charge, but essentially it's going to be moving either downward or upward. And so the magnetic field can be created to cause a second force from the magnetic field to oppose that electric field force. And in order to do that, they have to be equal and opposite. So that's where we would set them equal to one another. And in setting them equal to one another, we can isolate the magnetic field, and that's how we would solve for the solution in this case.